Hello. So hijacking the control flow of an executing program at the lowest level has been one of the security issues for the past 15 years. My co-authors and I have developed real compiler-based defenses against these types of attacks, and that's what I'm going to be talking about today in enforcing forward edge control flow integrity in GCC and LLVM. So to begin with, what exactly is control flow integrity? Control flow integrity is a policy that says that the execution path that a program follows has to correspond exactly to a predetermined control flow graph path, usually based on the control flow path of a static program. So for example, here is a control flow graph for a program, and control flow integrity says that this path would be okay, and this dynamic execution path would also be okay, but this dynamic execution path would not be okay because it introduces a path that was not in the original program's control flow graph. So in particular, you want to verify that no attacker has modified the target address of a branch or jump instruction and thereby hijacked the control flow of a program. Now, how can a branch target be attacked? Normally, you would expect the target of a branch instruction, like this conditional jump instruction, would be hard-coded in the text of the program and stored in non-writable memory. This is called direct control flow. However, you can have things like indirect function calls where the target of a branch or a jump instruction is stored in a pointer on the heap. This is indirect control flow. Or you could have a function return address being stored on the stack. So the indirect function call here would be a forward edge in the control flow graph, and the function return would be a backward edge in the control flow graph. As you might have inferred from the title of this talk, I'm going to be talking about protecting forward edges or indirect function calls. So why are we focusing on forward edges in particular? So there's a long history of stack-based attacks, and there's a correspondingly fairly well-known set of stack-based defenses. Now these defenses are pretty well known, they're fairly widely deployed, and for the most part they are highly effective, with the upshot being that the stack these days is usually pretty well protected in mature and well-written code, and we're seeing fewer and fewer successful stack-based attacks out in the wild. On the other hand, when we look at these forward edge indirect call-based attacks, again, there are quite a few attacks, and there are quite a few defenses, but the defenses generally are less widely known, less widely deployed, and sadly, they are also usually less effective. So that, in fact, several of the most recent successful attacks that we have seen have been exactly of this type. Now, what exactly are we contributing to this area? We are contributing practical control flow integrity enforcement in production compilers, namely GCC and LLVM, for these forward edges. So in particular, we have integrated control flow integrity for forward edges into GCC and LLVM. We've implemented two different mechanisms with different precision and security guarantees. These mechanisms have no restrictions or simplifying assumptions. So anything that you could normally compile with GCC and LLVM, you can apply these mechanisms too. We have incremental compilation, dynamic library loading, the whole 9 yards. These mechanisms scale completely. We've applied them both to the Chromium web browser, which comprises over 15 million lines of C++ code and over 50,000 source files, as well as many dynamically loaded libraries and third-party plugins, and we've been able to apply them with no particular difficulties to this very large system. Our mechanisms provide very strong security guarantees, and they come with very low performance degradations. So what exactly did we do? As I said, we've implemented two different control flow integrity enforcement mechanisms. We've implemented vtable verification, which is in GCC 4.9, and we've implemented the indirect function call checker, which is in LLVM. We have also implemented a programming tool. This is not an enforcement mechanism, but it's the indirect function call sanitizer, and it is in LLVM. It is part of the undefined behavior sanitizer. And this doesn't enforce control flow integrity, but it does help programmers find errors in their code that could lead to successful attacks if they weren't caught and fixed. So vtable verification basically guarantees that for every virtual call in a C++ program, the vtable pointer used for making that call is valid and correct for the static class of the type making that call. The indirect function call checker is a little bit less precise, but it forces every indirect function call in the program to go through a specially constructed jump table that it builds at compile time, and this jump table is therefore in the text non-writable section of the program and cannot be overwritten, and therefore this prevents attackers from changing the target of an indirect function call to anything outside of the program. The the indirect function call sanitizer verifies at runtime that the actual function signature of an indirect function call exactly corresponds to the function signature at the call site. Now, I'm not going to have time to go into a lot of details, or all of the details of these mechanisms, so I'm going to talk very briefly about one interesting aspect of VTV and one interesting aspect of IFCC. So in order for vtable verification to meet its very high precision guarantees, namely that the vtable used for making the indirect function call is actually correct for the class of the object making the call, vtable verification needs to have complete information about the entire class hierarchy of the program. Now, this seems to be in direct conflict with our statement that we can perform incremental compilation, because when you're doing incremental compilation, you can only see what's in a single source file at any given time. The way that we dealt with this problem is that we broke the work up into two different pieces. So at compile time, we have the piece that looks at the file that we're analyzing and collects all the class hierarchy information and vtable pointer information that it can find in that file, and it stores these pieces of information in the object files as it generates them. We then have a piece that also works at runtime. So in a C++ program, what happens is you start the program, and then you load your libraries, and then there's a bit that runs the constructor functions for all the objects that need to be built before the main program starts executing, and then you start executing the main program. And what we've done is we've added a runtime library to GCC called Llvm, and this library runs before the constructor functions that run before main, and it collects all these bits and pieces of class hierarchy information, vtable information that we assembled in the object files, and it puts it into a complete class hierarchy data set so that we can use this for performing our verification. Also, during program execution, if we load a dynamic library, again, the dynamic library has these constructor functions that run before it actually starts running, and libvtv will run before these constructor functions, and again, it will collect any class hierarchy information that we found in the dynamic library, and it will add that information to our data sets as we're performing the verification. Now, the verification itself is relatively straightforward and pretty much what you would expect. We insert a verification call before every virtual call that checks and makes sure that the vtable pointer that's about to be used for making that call is in the set of valid vtable pointers for the class of the object. Now, verification in IFCC works quite differently, and that's what I'm going to talk about next. So to understand IFCC, you consider indirect function calls. Here we have a register RAX that stores the address of a function f. For every such function f that is used as the target of an indirect function call in the program, IFCC creates an entry in a new jump table, in this case f_jt. The jump table, now in this example we have one single jump table, but IFCC is actually written in such a way that it allows programmers to specify how they want to partition the functions into jump tables. One implementation that we tested was partitioning the functions into jump tables based on the number of arguments at the call site. But in any case, the jump table gets padded to a size of 2 to the n for some value of n, which is important because we then use that for pointer bit masking. What happens next is that IFCC goes through the source program and finds every place where the address of function f is taken, and it instead uses the address of the entry for f in the jump table, namely the address of f_jt in this case. And it also goes through and finds all the call sites for the indirect function calls and modifies the pointer so that it is forced to point into one of these jump tables, and that's using the pointer bit masking that I mentioned earlier. There's a new version of IFCC that's currently being upstreamed into Llvm that not only updates these pointers, but also does some checking on these pointers similar to the manner of VTV. Now that's all the detail of the particular implementations I'm going to talk about. The next thing that we're going to look at is how well do we actually do. So when you're looking at these types of things, the two things you're really interested in is, well, how secure are you? Did you really do the job you were trying to do? And what kind of runtime performance penalty are we going to be paying for doing this? Now, security is a very hard thing to measure, so what we did was we looked at the AIR metric, the Average Indirect Target Reduction metric that was introduced at the Unix Security Conference last year. And this will tell you roughly the fraction of indirect control flow instructions that are protected by the particular mechanism that you're looking at. Now, we modified this metric slightly to come up with what we call the FAIR metric, which stands for Forward Edge Error, and that's because obviously we're not interested in all the indirect control flow instructions, but only the forward edge ones. So then we calculated the FAIR metric for both VTV and IFCC on the Chromium web browser, which we compiled with our implementations. For the runtime performance degradation, we looked at the spec C++ 2006 benchmarks and also the Chromium web browser running standard browser benchmarks, Dromeo, Sunspider, and Octane. And then, of course, we built the benchmarks with and without VTV and with and without IFCC and looked at how they performed. And this table gives you an overall summary of how everything compared. So for security, as you can see, VTV got a fair metric of 95.2%, and IFCC actually got a fair metric of 99.8%. Now, it's not surprising that VTV had a lower fair metric because VTV was not attempting to protect all the indirect function calls. It was only trying to protect the virtual calls. But the fact that we actually got 95.2% underlines a very important point, which is that in C++, by far the vast majority of the indirect function calls are indeed virtual calls. The remaining forward edges that we did not protect with VTV, most of them turned out to be either C-style indirect function calls or indirect function calls that were in statically linked C libraries. And in IFCC, they were almost all in statically linked C libraries. Now, looking at the performance penalty, the first thing you need to understand is that in this kind of mechanism, you are going to have some kind of performance penalty because we are adding instructions to the execution stream, so it's going to have some effect. The actual amount of performance degradation you see is going to depend on the dynamic characteristics of the program that you're verifying. If you're doing a program that makes very few indirect function calls, then you're going to see a very low performance penalty. And if you're doing a program that has a vast number of indirect function calls, you're going to see a much higher penalty. Now, our performance penalty ranged anywhere from 0.6% up to 9.1%. In all cases, it's below 10%, and in most of the cases, it was well below 10%. Mostly, we saw things in the range of 2 to 5% degradation. The two different metrics that you see for IFCC are one where we implemented just the single jump table, and one where we had jump tables that were partitioned based on the number of arguments. Now, in terms of precision guarantees, as I said before, VTV is our most precise mechanism. It guarantees that the target of a virtual call is actually in a correct class for the call site. IFCC is a little bit less precise. It guarantees that the target function of any indirect function call, sorry about that, just a second. It guarantees that the target of an indirect function call is going to be a function that was in the original program that we used for an indirect function call. And if you're using the jump tables based on the number of arguments, then it also guarantees that you're calling a function that has the correct number of arguments. FSAN, our tool, guarantees that the target of any indirect function call has the correct function signature, but it doesn't say anything about whether it was actually in the original program or not. Again, this is because it's not an enforcement mechanism, but a programmer tool. Now, vtable verification can be applied to any C++ program, and it verifies only the virtual calls in the C++ program. IFCC can be applied to any program that Llvm compiles because it's all in the back end. It doesn't depend on the language at all. And it also tries to verify all indirect function calls. And FSAN falls in the middle of these two. You can only apply it to C++ programs, but it does verify all of the indirect calls in that program. So the next thing I'm going to talk about is some of the software engineering issues that we ran into when we were implementing these and some of the lessons that we learned. So one of the things that we found out was that fully integrating control flow integrity with the compiler significantly helps with performance. And this is because, of course, it allows you to take full advantage of the later compiler optimization passes, and your verification code gets optimized as well as the rest of the code in the program. Now, the flip side of this is that it becomes very important that when you do your security analysis on the output, you actually look at the final output of the compiler and not at any of the intermediate stages, such as the pass right after where you did your verification. And this is because later compiler optimizations may be perfectly fine from a correctness point of view, but they may actually undo some of your security and verification code. And actually, when you're writing your security and verification passes, you need to be aware of this type of thing and try to write your pass in such a way that it makes it harder for the compiler to undo it later with other optimizations. We also found that incremental compilation actually makes things much more difficult. If you allow for incremental compilation, then again, the compiler is only going to see what's in the current file that you're looking at, and this can lead to incomplete data, which in turn can lead to false positives. In our case, when you have a false positive, that's going to cause execution to abort because we assume the program has been attacked. And having perfectly fine programs aborting on you is completely unacceptable. We had to find a way to avoid this at all costs. So the way that we dealt with incremental compilation was with IFCC, all of the work actually occurs in the link time optimizer, And as this diagram tries to illustrate, by the time you get to the link time optimizer, you have the whole program information, so the incremental compilation is not so much of an issue. And as I mentioned earlier with vtable verification, the way we dealt with this was by actually splitting the work into two parts. So we have this runtime library piece that actually does have the whole program that it can look at and deal with when building the data sets, et cetera. We also found that it is necessary to be able to support dynamic library loading because out in the real world these days, purely statically linked binaries are becoming very hard to find. A corollary of this is that you have to be able to deal with the fact that you are going to be dealing with libraries and third-party plugins that you could not compile with your mechanism. You just don't have access to the source code, and so you're going to have to deal with mixed verified and unverified code. This can be another source of having incomplete information, and again can lead to false positives and incorrect program aborts, which again is not acceptable. Sadly, the only way that we found to deal with this was to actually allow the programmer to be able to intervene. There was no automatic mechanism that we could figure out that would allow you to deal with this. So in IFCC, what we do is the programmer is allowed to explicitly specify certain functions that the programmer does not want verification to occur in. So if the programmer knows that a particular function is going to be making these indirect calls into a library that's not verified, we just say don't do the verification here. vtable verification took a slightly different approach. It actually allows the programmer to overwrite the default failure function. So the default failure function normally would say, we couldn't verify this pointer, we think you've been attacked, let's go abort, and it would abort. And the programmer now has the option of going in there and replacing that with a function that, say, has a whitelist of libraries that it knows wasn't verified, and could even, if desired, do some secondary, maybe less precise verification of those libraries that it can do without having access to the source code. Anyway, there are a lot more details that are in the paper, but that's all that I've got for now, so I'll take any questions. Yeah.
Yeah, thanks for the very interesting talk. My name is Luca Davi from TU Darmstadt. I'm a bit concerned about the security model that is behind this work. So consider we have an application like Firefox or Adobe Reader. So how does your system prevent an attacker from abusing an indirect jump or a call to call, for instance, a critical function like virtual protect or virtual alloc?
The attacker can only make that kind of function call. In IFCC, the attacker can only make that kind of function call if that kind of function call was made as an indirect function call in the original program. It has to be a function that was used for an indirect function call in the original program in order to be allowed by IFCC to make that call. And in vtable verification, unless that's actually in the class hierarchy of the object that's trying to make the call, it's not going to be allowed at all. So does that answer your question?
Yeah, thank you.
Okay.
Hi, this is Ali from Stanford University. So I was wondering, in IFCC, what I noticed is in the paper, you actually talk about just masking a set of bits and then adding them to the base, which gives attackers like a really cool tool to iterate through all the possible functions they could call, and then combined with the fact you don't protect return pointers, it seems like this is a lot of leverage for them that you're giving. Is there that much performance difference that you don't want to somehow check that they're actually pointing to the right pointer, or?
I'm not the best person to ask about that, actually. I didn't do the IFCC implementation. If Tom is here, maybe he would be the best person for you to talk to about that, probably okay. After the main
Sure.
talk.
Raphael, thanks a lot for releasing this. This is awesome work. But my question is that you were claiming that if you had a binary and you couldn't lift it, so I was wondering if you looked at the possibility of losing a library that can lift the binary to Llvm, and what are you think some of the challenges of applying this technique to lifted binary code?
I'm not sure what you mean by lifting.
So if you take an x86 program, right, and you lift that into the Llvm IR, right?
Yeah.
And then from there, do you think that these two techniques could be applicable at that level? Instead of at the source code level, you lift it to Llvm.
Well, these techniques are applied in the compiler, so Llvm is doing its work at the intermediate representation level, and so is VTV. VTV is just doing it largely in the front-end representation of the program.
Okay.
But they are happening in the compiler intermediate representation.
Okay.
Nick, one last question while Vasilios sets up. And if no one else jumps up to ask one, I will. So it sounds like this is a great result and something very practical. How close are we to having the next version of Chrome compiled with this built in, or are there hurdles left before it could be in a release like that?
There are a few things that we are still working on, but that is definitely the final goal, is to have Chrome built with this automatically enabled. So that's all I can say at the moment.
Okay,
But
thank
we're
you.
working on that,
Let's
yes.
thank Caroline again.